Good morning and welcome to IAME's 35th Annual Training Seminar. My name is Jason Ustashevsky. I own and operate a marine surveying company called Cape Marine Survey located in Cape Coral, Florida. Cape Coral is a suburb of Fort Myers. Cape Coral is approximately 3 hours south of Tampa and 2 hours north of Naples. I am an accredited marine surveyor with SAMS, an AVYC master technician, and a CMI with IAME. I was a technician for almost 20 years before getting into the field of surveying. Because of this, I'm a little more hands-on than the customary surveyor. Cape Marine Survey offers services ranging from inspections and surveys of vessels to troubleshooting complicated engine, electrical, and corrosion-related issues. I've also worked with Doug & Company at Pilot Marine Survey for years, and I'm proud to be part of their family. Pilot Marine Survey's specialty is marine damage claims. My presentation this morning is about electrical event investigations and complicated bus system diagnostics. I like to use the word electrical event compared to lightning and power surges because an electrical event can range from direct or indirect lightning strikes, power surges, but also include specific failures that can be caused by battery charger failure, power inverter failure, generator output failure, shore power problems, battery polarity reversal, incorrect diagnosis, and more. This presentation mainly regards bus systems, which are communication systems that are found in most modern transportation vehicles, including recreational and commercial marine. My apologies up front. This will be a little technical, but if you hang with me, I think you will all learn something. There are different types of bus systems, including but not limited to CAN bus, LIN bus, K-line, and more. This presentation will focus on CAN bus and versions of CAN bus, which are the most widely used. The term CAN bus is an acronym made together of two separate acronyms. The first part of CAN bus is CAN, which stands for Control Area Network. Essentially, it's a local network. The second part of CAN bus is the bus. The bus is a data highway, a data bus, a communication system that transfers data between components. Some people may refer to this as a trunk. CAN bus is a local computer network designed to be used in vehicles. CAN bus started in 1983 at the Robert Bosch Company in Germany. The protocol for CAN bus was officially released in 1986 at a Society of Automotive Engineers conference in Detroit, Michigan. The first CAN controller chips were introduced by Intel Company in 1987. The first automobile to have CAN bus was the 1991 Mercedes-Benz W140. Today, CAN bus is used in everything. It's used in automotive, aerospace, aviation, agricultural, marine, and more. Shown in the diagram is a CAN bus system for the typical automobile. The automobile may have components such as an engine computer, an instrument cluster, a climate control system, an anti-lock braking system, an airbag, and a body control module. The CAN bus system is a computerized network system that allows these individual components to communicate back and forth at high speed in real time. CAN bus also allows for digital switching, which means soft touch buttons. If you remember your automobiles that you drove from approximately the mid-1990s on down, unless you did have that 1991 Mercedes W140, you probably remember that the controls for your heating and your air conditioning were very clunky switches. Your controls for your power door locks were clunky switches. You had no airbags. You had no anti-lock brakes. You had no body control modules. CAN bus has enabled these technologies to emerge. CAN bus is now used in recreational and commercial marine. It allows components including but not limited to chart plotters, compasses, radars, depth sounders, engine, data modules, and more to communicate in real time, similar to a modern day automobile. Well, CAN bus was invented by the Robert Bosch Company and adopted by the Automotive Society of Engineers for the automotive industry. NEMA, which stands for National Marine Electronics Association, has adopted their version of CAN bus to be used in recreational and commercial marine applications. NMEA, pronounced NEMA, has two communication protocols or two communication systems that they use aboard commercial and recreational vessels. The first protocol is called NMEA 2000, which is sometimes referred to as N2K or NEMA 2000. This is a two-wire communication system which allows communication between various components in vessels. NEMA 0183 is an older version of NEMA, which uses a four-wire system. NEMA 0183 is still used in recreational vessels, however, not common. NEMA 0183 is still in common use in commercial vessels. While CAN bus systems are reliable and robust, they do have an Achilles heel. Their Achilles heel is that when the CAN bus system fails or ceases to work, they are extremely difficult to diagnose and troubleshoot effectively. Because of this, most non-educated repairers elect to replace the entire system with a new system versus trying to troubleshoot and repair the existing system. Because CAN bus has this Achilles heel and is notoriously difficult and technical to troubleshoot when it fails, as an adjuster, when you have an insurance claim for a lightning strike, power surge, or some other electrical event, who are you going to call on your behalf? When your insured tells you he's had a repair person look at the vessel and has a 5 to 6 figure repair estimate, again, who do you want looking at this vessel on your behalf? Who you want is somebody with years of experience investigating electrical related claims, ideally an ABYC marine electrician or better. Extremely complicated claims may require the use of marine electrical engineers and also engine dealerships who have the test equipment to diagnose incorrectly or non-running engines that may or may not have been damaged by an electrical event. I can promise you this. I am all but certain I know who the insured called to look at his boat and who generated that repair estimate. Your insured hired a person called this guy. This guy is the guy I run into in the field. This guy is the guy who tells me the boat was hit by lightning when there's no evidence of a direct lightning strike. This guy is the guy who tells me there was a side flash or lightning hit the boat next to it, or we have all of these components on the subject vessel that aren't working, but this guy is certain it was lightning because it could not possibly be anything else. When you receive that repair estimate for an electrical event, a good portion of that estimate is going to be for replacement of the vessel's electronic system. Replacement of the electronic system is usually performed by an NMEA or NEMA certified person. However, when you go to the NEMA website, you will see 4 classifications for certification. The 2 on your left, which show MEI, stands for Marine Electronics Installer. There is a basic and advanced marine electronics installer, which revolves around the 0183 NEMA protocol. On your right, you will also see a basic and advanced NMEA 2000 or N2K installer certifications. What you want to remember are these are installer certifications. They are not technical certifications that teach the person how to effectively troubleshoot and diagnose why marine electronics are not working, nor articulate an opinion as to why they have failed. When investigating a vessel for the first time with the claim of an electrical event, there's going to be damage components that are customary to lightning strikes, power surges, be it direct or indirect. Anything with a diode is customarily damaged. A diode is a type of semiconductor found in AC and DC electrical systems. In a DC electrical system, a diode allows voltage to travel in one direction and blocks voltage when going in the opposite direction. In an AC electrical system, a diode converts AC electricity into DC electricity. Many components use diodes. LED, which stands for light emitting diode lights, use diodes. Circuit boards use diodes. Charging system components, including the voltage regulator inside of an alternator or the voltage regulator on an outboard engine, use diodes. Battery chargers, power inverters, modern electronics, including televisions, stereo systems, and marine electronics, use diodes. Engine computers use diodes. Fly-by-wire communication components use diodes. If a vessel is directly or indirectly struck by lightning or suffers a severe electrical event, a diode is a very common component to find damaged. There's also components which are not customarily damaged during an electrical event. Anything that contains electrical windings, and these are found in starter motors, utility pumps, alternators, windlass motors, bow thruster motors, and more. These items are customarily not damaged during an electrical event. I've done inspections on vessels where the repair person has a line item on their estimate for a replacement windlass. I inspect the windlass and I find the contactor, which is a form of a relay, is corroded to pieces, and the windlass will function after the contactor is replaced. I've been on inspections where the bow thruster does not function, and it's as simple as the circuit breaker is turned off for the bow thruster. It needs to be turned back on for it to function. Engine fuel injection components, including fuel injectors and ignition coils, do not contain diodes, and these components customarily are not damaged. Part of basic troubleshooting is simply getting a lay of the land. When I step aboard a vessel for the first time for an electrical event investigation, I take a piece of paper and draw a line down the middle. On one side of that line, I start including items that are customarily and expected to be damaged during an electrical event, such as a direct, indirect lightning strike or a power surge. On the other side of the line, I start writing down items that are not customarily damaged during an electrical event, including a lightning strike or a power surge, be it direct or indirect. After I have my items written out, I'll look at the items and see if the vessel is overall presenting as a vessel that was damaged during an electrical event, such as a direct or indirect lightning strike, or if evidence is showing that there's something else going on with the vessel and maybe the vessel was not directly affected by an electrical event. After performing some basic troubleshooting and getting a lay of the land, the next step is diagnostic troubleshooting. When you receive a repair estimate from a repair person, a good portion of that repair estimate usually includes replacement of the vessel's entire electronics package. It is not uncommon to see figures in the $30 to $40 to $50 or $60,000 or more for replacement of everything, with very little money being spent on troubleshooting of these components to determine if they are faulty, and if they are, why they are faulty. On the backside of every single piece of marine electronics is what's called an NMEA or NEMA port, which is marked by the red arrow in the photo. A NEMA port is similar to a modem port or a router port. A cable is connected to the NEMA port on the back of any piece of marine electronics, and that cable runs to T-fittings and adapters which connect to the main backbone of the CAN bus system. Marine electronics can fail in a number of different ways. The first way is the device simply does not power on. If the device does not power on, the second step is to remove the power cable from the device and ensure that both battery power and battery ground are present, and also ensure that the polarity is correct and not reversed. If the device blows fuses upon connecting the power cable or upon attempting to turn the unit on, we know power and ground are going to be present at the unit, but it still needs to be checked to determine that the polarity to the unit is not backwards. If we have a device that does not power on, or a device that blows fuses, and we verified that battery and ground are present and that the battery is connected correctly and the polarity is correct, the device can be condemned. However, we cannot give an opinion as to why the device is non-functional at this time. If the device powers up, the network port, the NEMA port on the back of the device can still fail in a number of different ways. This port can fail by having excessively high resistance. This port can fail by having a short circuit. This port can fail by not outputting or inputting data from other components, or this port can fail by outputting noise, outputting a signal that overwhelms the other components on the network, rendering the other components incapable of talking to each other until this electrical noise is removed from the network. I showed this slide earlier in the presentation, but wanted to bring it up again. This is a customary installation on a recreational marine vessel. In the photo, you will see components including the chart plotter, the wind transducer, the radar, the GPS, the engine monitor, battery monitor, and more. Part of the Achilles heel of the CAN bus style system is that if any one component has a NEMA port that has excessively high resistance, this crashes the CAN bus / NEMA network, and none of the components will talk to each other. If any NEMA port has a short circuit, it will crash the network. If any port is injecting noise into the system, it will crash the network, and the remainder of the components in the network, while functional, will not be able to speak to each other until the crash is identified and remedied. The other thing you want to keep in mind is sometimes the components themselves are actually fine, but there's a problem with the wiring, or what's called the terminators, which are resistors which set the resistance for the network. Sometimes there's no electrical event at all. Sometimes a critter gets in there and starts chewing the wiring and creates a short circuit in the wiring or an open circuit in the wiring. When that happens, the network and all of its components will power up, but the components will cease to function to speak to each other. To the average NMEA installer and not a technician familiar with the components and how they work and how they communicate and how to test that communication, the average non-trained installer will perceive this as a lightning strike. To test these NMEA CAN bus systems, there are required tools. Not only are the tools required, but the knowledge to use them effectively is also required. The required tools are a quality multimeter or DVOM, digital volt ohm meter. An oscilloscope is required. A tool called a nav doctor, while not required, can greatly reduce the amount of time troubleshooting an NMEA / CAN bus system. A nav doctor is similar to a scan tool for NMEA networked marine electronics. Required tools are also network cables, spare terminators, spare fittings, spare adapters should always be brought with whomever is inspecting or troubleshooting the system. Additionally, breakout harnesses or adapters are also required to gain access to take measurements from the NMEA / CAN bus system. Additional tools also include a decade box. A decade box is a type of variable resistor box that is not for CAN bus systems, but will help assist in troubleshooting and diagnosing other items that are commonly claimed as loss related during an electrical event. Diagnostic scan tools for marine engines are also required should the engine be non-functional. Most importantly, an education and a desire to troubleshoot the problem and not just replace parts are the most important tools in the toolbox. These are commonly used tools that I bring along with me with every electrical investigation that I perform. Shown in the photo is an oscilloscope made by a company called Pico Technologies. Pico makes quality mid to high level oscilloscopes which allow us to see what is going on inside of the CAN bus system. High quality multimeters are also required. This meter shown in this photo is almost $600. The average meter that the average technician brings out is usually the cheapest thing they can find from Amazon or Harbor Freight. This is a nav doctor. A nav doctor ties in to the NMEA 2000 network and displays data on a laptop or computer screen, similar to how a scan tool would display data for an engine. You also need to bring along cables, backbone cables, terminators, adapters, and every fitting conceivable in order to rule out the possibility that the subject vessel does not have a component problem, but has a fitting problem or adapter problem or cable problem. This is a decade box. A decade box is a variable resistor. It helps in troubleshooting certain types of analog style gauges. This is a breakout box for a Mercury marine engine. Marine surveyors will not have breakout boxes for engines. However, high quality dealers should have these breakout boxes as part of their toolkits. Low quality dealers may not have these types of breakout boxes. If the vessel is at a low quality dealer, it is usually recommended to have the vessel moved to a more qualified repairer, as troubleshooting engine-related faults without these breakout boxes can be cumbersome and lead to incorrect diagnosis. This is an example of another breakout box for a Volvo Penta diesel engine. The above photos represent thousands and thousands of dollars worth of diagnostic test equipment. I hate to beat up on this guy too much, but this guy, who is the expert the insured brought on his behalf, is not going to have access to this equipment. If I loaned him this equipment, he would not know how to use it, nor how to interpret the results of what he's seeing. Because of this, the insured's experts, their guy, will often have multiple incorrect diagnoses. Let's talk about diagnostic troubleshooting of CAN bus systems. This is a table I set up in my living room for the purpose of creating this presentation. However, I can perform the same diagnostics aboard most vessels. In the photo, you will see 3 chart plotters, a power supply to power those chart plotters, a laptop, network cables. There's a nav doctor diagnostic tool in there someplace, and other tools that I use to troubleshoot these systems. In this photo, we have 4 components that are capable of connecting to the NEMA network system. Of those 4 components, 3 of them are chart plotters. The 4th is the nav doctor diagnostic tool. Additionally, I have an oscilloscope connected to the network to read the data coming out of these components. This is a screen of one of the chart plotters connected to the NEMA network system. The red arrow in the photo points to what is called the device list on the chart plotter. Any NEMA system component that has a display screen, such as a chart plotter or an autopilot display, or various other components, will often have what's called a device list built into their menu system. The device list is nothing more than all of the devices on the network that this specific component sees and is able to speak with and share data with. In this photo, the only item shown on the device list is the actual device itself, and it's not capable of communicating with the other three devices, which include the other two chart plotters and the nav doctor on the system. The first step in troubleshooting any NEMA or CAN bus style system is to check the resistance of the network. The resistance is controlled by what are called terminators, which are resistors that provide an appropriate amount of resistance for the circuit to function normally. In a standard CAN bus or NEMA system, the resistance must be 60 ohms of resistance. If the resistance is excessively low to no resistance, there is a short circuit in the network. This short circuit can occur on any cable, or it can occur in a device itself. If there is an excessively high amount of resistance on the network, this means that a device has excessively high resistance on the NEMA port, or there's corrosion or poor connections in the connectors that make up the cabling for the NEMA system. If there is no resistance shown and the circuit is open, this means that there is a break in the wiring on the main backbone or trunk for the NEMA system. The next step after checking the resistance of the network and verifying it's correct is connecting the oscilloscope to the network and seeing what I'm getting out of the network for voltage. And not so much voltage, but seeing what I'm getting out for data. Now, NMEA is a version of the automotive CAN bus system that's used in automobiles. What we're seeing in the photo is a waveform that does not resemble a CAN bus waveform nor an NMEA waveform. What we're seeing is a waveform that's being generated by a faulty component because the NEMA port is spitting out noise. And this is what the noise looks like. It's an erratic pattern on the oscilloscope. In our previous slide, we confirmed that the NEMA network has noise that's being injected into it by a faulty component. The next step in the troubleshooting process is determining which component or components is injecting that noise into the system. The next step is removing one of the chart plotters from the network and retesting the data signal from the network to see if it's changed, stayed the same, or has become consistent with the CAN bus / NMEA waveform. And what we'll see here is that the waveform has certainly changed, but it has not gotten any better, and it does not resemble a standard CAN bus / NMEA repeating waveform. What that tells us is, one, we still have a problem, but two, because the waveform did change from the previous recording, we can confirm that the component we disconnected is faulty and the NEMA port is injecting noise into the system. Now, if we want to triple check that, what we can do is disconnect all other remaining components from the NEMA network, connect the suspect component, resample the waveform, and see if it's the same as the one shown in the previous slide. If it is, and it would be, it's a confirmed bad component. What you're looking at in this clip is a standard CAN bus style / NMEA acceptable waveform consistent with what is expected to be normal. What we see here is a repeating consistent pattern of voltage across the network. The peaks and valleys in the pattern represent binary code, ones and zeros. These components are sending ones and zeros to other components to be deciphered and interpreted, whereas the opposing components will send ones and zeros back to the original component for additional communication. As the waveform shown in the previous slides has corrected, it is no longer erratic. This proves that the previously disconnected components were faulty and injecting noise into the NMEA network, preventing the remaining components on the NMEA network from communicating with each other. If the pattern shown in this video was erratic, we would still have a problem that was yet to be diagnosed. This is the same device list shown in a previous photo. In this photo, we have the device for the chart plotter, but now we also have the device for the nav doctor. This means that this chart plotter is now communicating with the nav doctor tool and vice versa, which it could not do with the two damaged chart plotters connected to the NMEA system. This is a very rudimentary diagram showing a NMEA network system connected to an outboard engine using what's called a junction box or an engine interface. If we have a situation where the engine is not functioning correctly or the engine's not starting, and we also have NMEA network components that are not functioning, the very first step is removing the junction box, removing the engine gateway, and physically separating the engine from the NMEA network to determine if the cause of both failed items is due to the junction box or not. Okay, I know I'm running a little shorter on time, so we're going to do a couple of just quick case studies of what we actually see out there in the field when we do these direct, indirect, lightning strike electrical event claims. Case study 1, indirect lightning strike. This comes from the repair estimate from the insured's repairer. Quote, diagnose Yamahas not starting and gauges not rocking. We hooked our computer to it and had no luck. We believe the boat could have been struck by lightning due to the fact that the Optimus and Yamaha systems both failed at the same time. Well, if the repairer says it's a fact, it must be true. And I think the number on this estimate, I don't know, it was like $30,000 for everything. So I go out and take a look at the boat, and this is what we see. So this is an example of what's called a Yamaha DEC, or digital electronic controller. It's the throttle shift lever for the engine. It is an electronic throttle shift lever, meaning it's a fly-by-wire system. There's no cable. This shifter sends a signal back and forth to the outboard engine. Now, when the key was turned on this claim, the red light was blinking on the throttle control, meaning the throttle control was not responsive. Now, when I connected my scan tool to the engine, it did not communicate. I had no luck either, just like the repairer said he had no luck. But since the throttle control was not working, that can interfere with the data signal between the throttle control and the engine, preventing engine communication from the engine's ECM. So my next step was simply unplug the throttle control and see what happens. And that's exactly what we did. Is I unplugged the throttle control, and then all of a sudden the engine came back to life. We couldn't start it because it didn't see a throttle control, and it wouldn't allow us to start it without one. But we did see that the engine computer is functioning and it's outputting correct data, which means the recommendation from the repairer to replace two engine computers is not a correct diagnosis. This is the Optimus C-Star system the repairer was speaking about on his estimate. This is part of a power steering pump system. There's no physical damage to the front of the unit. When you look at the back of the unit, there's a circuit board in there, and it's potted in rubber. And you'll see a little overheating hole on the bottom left-hand corner. And there it is zoomed in. So really what we had is we had a remote control that doesn't work, and we have a little overheating hole and a pump control module, which is a device that draws a fair amount of electrical current. And any device that draws a fair amount of electrical current is going to create some heat. So going through the boat further, the repairer, the insured's guy, stated the gauges were not rocking. All of the gauges worked. We had no issue. And what we were left with is a vessel that has a power steering electric pump control module that's been overheated, and we have a throttle control that is not functioning. The rest of the vessel, all the electronics, they all power up. They all communicate. There's no issues there. They communicate with the engine. There's no issues there. So do we have an electrical event, a lightning strike, a side flash, or do we just have one or two components that failed over time? Next case study is an indirect lightning strike. This was on a sailboat, and the insurance repairer pulled out. What we're looking at is a control board for one of the air conditioning systems. And on the right-hand side, the red arrow points to a lot of soot on a capacitor that's inside of the air conditioning control board. And really what we have here is the cap blue. The cap overheated and blew, and that's why we see all the soot. Now, having a look at the boat, one thing we noticed was the shore power cord was it was disconnected. Not disconnected, excuse me, it was corroded. It wasn't the worst one I've ever seen, but it wasn't the best either. And with electricity, with AC electricity, when we have corrosion in the circuit, that corrosion creates a drop in available voltage to whatever we're trying to power up. In this case, it was an air conditioning system. Now, if we have a drop in voltage, that component's going to want to try to draw more current to compensate for the lack of voltage. Now, the more current we have running through any component, the hotter it's going to get. And although this is not this claim, we've all seen this before. What happens when corroded shore power cords are being left in service for too long? They melt down because of the current and the heat going through the wire. But that's not this boat. So I'm going to the boat further, and I find the main circuit breakers for the boat, and somebody's been in there recently doing something because they are not original to the boat, and they're missing the face covers. And they're also really not connected very well when you looked at them. So I was speaking with the repairer who stated the boat was struck by lightning, and he said, yeah, we were having some intermittent electrical issues with the shore power system. Excuse me. But before this lightning strike happened, and I said, okay. And I know why they replaced these, and that's because the corrosion in the shore power cord was causing the original breakers to trip. Next we get to the electronics in this gentleman's vessel. And I had a repair estimate for replacement air conditioning system. I think there was a replacement power inverter. And then all the electronics. I think there's about 10 or 12 pieces with this one. And they all powered up except for one. One did not power up. We removed that component. We did verify it had power and ground, so we just had a dead component. But the remaining 10 components or so, they wouldn't talk to each other. So I break out my tools, and what do I find? I find high resistance in the NEMA network. So the next step is to try to locate the source of that high resistance. And after digging around for about an hour and a half, lo and behold, somebody at some point in time had taken a NEMA network cable and cut it in half and spliced it back together. Now, these cables are shielded. They're not designed to be cut and spliced. Additionally, although it doesn't show it in the photo, there is some corrosion inside of these electrical connectors, creating excessive resistance in the system. So while I know I have about 10 components that don't talk to each other, I don't know why, but now I know that I have excessive resistance, and that can cause the components not to talk to each other. So the next course of action is to correct the high resistance problem and retest. So we cut these butt connectors out, we strip the wiring back, we strip some of the corrosion back, and put new connectors on temporarily, only temporarily, because the correct course of action is to replace the wire, and go and retest the system. And what do you know? Son of a gun, I still had high resistance. I thought that was going to fix it, but it didn't. So I go digging around some more, and what do I find? I find a NEMA adapter located down in the bilge of the boat, always getting exposed to salty bilge water, and the connector that's exposed is corroded. Now, this is why it's important to bring test connectors with you. The repairer didn't have one. They're not terribly expensive. They're $30 or $40, but I carry one with me. So what we did was we unscrewed this from the boat. We pulled it out of the bilge water. We disconnected the 3 wires from it, and the wires looked good. All we saw was the corrosion in the one terminal. And so I put my test or my replacement fitting in place of this corroded fitting. And what happened next? What happened next is my NEMA resistance went from high back to the 60 ohms it was supposed to be. And every single item, except for the one item that would not power up, everything started functioning again as it should. So we had $40,000 or $45,000 worth of replacement electronics on this vessel. Due to a reported lightning strike. There was no visible evidence the vessel got struck by lightning. But what did we really have at the end of the day? We had a corroded shore power cord that was causing circuit breakers to trip. We had a corroded shore power cord that was causing excessive current draw through an air conditioning control module. There was no evidence of any kind of electrical event caused by lightning, be it direct or indirect. Excuse me. All right, flying through, last case study. This was the same boat. Excuse me. This is the autopilot controller. I was looking at this one, and the fuse looked burnt. When looking at it from the backside, I could see it was overheated. But the autopilot was powered up, and I was trying to figure out how it was powered up when the fuse looked like it was burnt. And so I pulled the fuse out, and lo and behold, somebody wrapped copper wire around the terminals. So I guess this insured was having a problem with this autopilot pump as well at one point, and the fix was copper wire on the fuse terminals. Always a solid solution. One more thing in this vessel, and this is to bring up the decade box. The insured was saying his water level sensors for his waste tank weren't functioning, and they thought it was loss related. Really, what happens with this boat is the boat sat unused for like 8 or 9 months, and nobody's been out to the boat, so it just sat there with the shore power cord plugged in, the air conditioning system running until the breakers would trip, and then when the breakers would trip, the repair guy would go over and thinking he had a breaker problem, he replaced those when he really had a shore power problem. But the claim was that lightning damaged the water level indicators in the boat for the waste tank and the freshwater fill. So there's sending units that go along with these gauges that provide a signal as to how full or how empty these tanks are. And there's kind of 2 ways to test the system. The first way is you can pull the sending units out, and you can test those independently of the actual display screen with the multimeter. But the problem is they're hard to get to. They're not easy. It's going to take hours and hours of labor to get it out. One's in a freshwater tank, so that's not going to be terribly bad to manipulate to test it. But the other's in a waste tank, and ain't nobody got time for trying to test this float switch in a waste tank. You just don't want to touch it. You want to pull it out and throw it in the trash, not caring if it's good or bad. So what we can do is we can test the display monitors, and we can do that with this Decade box. And I don't have a video of me showing it, showing how to test the display monitor, but I do have a video showing how to test a very basic analog fuel gauge, which is just a level gauge. It works the same way as a waste level gauge or a water level gauge. They all work the same way, and we test these things by connecting the Decade box to the gauge, which is a variable resistor, changing the resistance and seeing how the gauge reacts. At a specific resistance, the gauge is supposed to be empty. At a specific resistance, it's supposed to be half full. At a specific resistance, it's supposed to be full. Using this Decade box is one way we can test that. Uh, Last but not least, this was another alleged direct lightning strike, but this one was actually a direct strike. So this one was directly struck at the mast. It was a sailboat. But unfortunately, this was the insured's repairer. This was that guy that he found. And he was nice. He was very nice to work with, very, very humble to work with. Gave me a six-figure estimate times two. And was just not very thorough. I mean, the boat was hit. And we had our customary and not customary damages. And this boat was another typical Florida boat where the boat's been sitting for months and months and months, if not maybe a year or more, never used. And when they sit that long, how do we really know what's not working due to lightning versus what's not working due to sitting or what's not working due to previous failure? So this boat did have all sorts of electrical problems. This is the not the helm station, but like the map station where all the electronics are. So I get out to the boat, and the repairer, that guy had removed everything. And it's like I'm trying to make sense of his wiring, seeing what went to what. On the left-hand side of the photo, you'll see a TV. The repairer said this was loss related. And that. It must not be working due to the lightning strike. So it wasn't a very big item. It's a $300, $400 TV. So do we spend any time troubleshooting that, or do we just glance over it knowing that the vessel was directly struck by lightning? Well, sometimes you have to put, that's a close-up of the wiring. It was a mess after he took it apart because I couldn't figure out what was connected to what after he took everything out. But just using this TV as an example that the repairer was saying was not functional. Well, do I want to spend a lot of time at my labor rate while the repairer is also charging his labor rate for something as inconsequential as a TV on a vessel that was confirmed directly struck by lightning? And on this TV, the insured's guy, the repair guy, did not do anything to troubleshoot it. And so I spent 5 minutes troubleshooting it. And what I found was the TV was connected to an outlet, which was tied to a GFCI outlet in the galley that was tripped. So we had no power to the outlet. Not a huge savings, $400, but when you go through it line by line and then say, well, wait a minute, if the TV works, well, what about the stereo? Well, the stereo is on the same plug. Well, now the stereo works. What about the Bose system? Well, the Bose system's on that same GFCI. Well, that's now working. So even if it seems, not necessarily, if it's not necessarily a high dollar item, it's still worth spending a little bit of time because you never know what you're going to find. Um, this was a grounding bus inside the vessel, and we had a lot of DC components that weren't functional. So my advice to my client, to the adjuster was, we do have a lot of low voltage issues here all over the boat that the repairer is claiming as loss related, but we clearly have a corroded grounding bus that was not caused by the direct lightning strike. The insured has to have his repairer correct this corroded grounding bus at his expense because it's not loss related, and then I have to go back with the repairer and retest. The repairer was claiming pumps, all of the utility pumps, all of the water pumps in the vessel, they weren't working, they were loss related. And on these pumps, when you powered them up, you'd hear them hum for about 10 or 15 seconds and it would trip the breaker. So this boat hasn't been used in 6, 8, 9 months, maybe a year. And I don't know how much you all know about pumps or electric motors in general, but when they don't get used, they stick. And when they stick, they will not turn. And when they will not turn, they trip the breaker. So what we have here is pumps that are slightly corroded and slightly leaking. The red arrow points to some water leaking out of the pump. But it's not that they're bad. They're not damaged. They're stuck. And the easiest way to attempt to unstick a pump, and I know this is going to sound rudimentary, but click on the breaker and get to the pump as fast as you can get to it before the breaker trips, and start tapping on it very fast with a very small metallic hammer, which will vibrate the internal motor. And if it's stuck, a lot of times it will free up. So on this boat, it was like a 50 or 55 foot sailboat. I think we had 10 or 12 pumps at $400 or $500 a pump that were all stuck. In every single pump, we were able to free up by tapping on it with a hammer, which allowed it to run. And then we just allow them to run for a little bit and then turn the switch back off. And after that, we could turn them on and off and they would work normally. They were not related to a direct lightning strike. Finally, the repair guy with this boat, he was very nice. He was very nice. Bless his heart, he was nice. But his certification, he was an NMEA installer. He had no ABYC background. He said, "Oh, I don't need all that." And one of the items on his list was the boat has an isolation transformer. And the repairer said he was working on the vessel, trying to troubleshoot the electrical system, and he spent the better part of 6 hours trying to figure out why the vessel had 120 volts but did not have 240 volts through the transformer. And he deduced that the isolation transformer was damaged during the loss. So I asked Mr. Repair, and I said, hey, look at, how do we know this thing is damaged, and how do we know it was damaged during a lightning strike? And he said, well, what else could it be? And I said, I see a lot of rust on this. Are we sure it's not corroded internally and all rusted up, and maybe that's why it's not working? And he's like, oh, no. He's like, it's only just a little bit of rust on the outside. It's not that bad. And I said, you're right, it's not that bad. And I said, what are we getting for voltage into this thing? Because we should be getting 240 volts plus 120 volts from a 240/120 shore power cord. And he said, I don't know what we're getting into it. I never checked. And I said, okay, well, shore power goes into the boat through the shore power inlet. There's going to be a breaker for the 220 side, 240 side, and another breaker for the 120 side. And I said, well, what do we get at the shore power cord? What's going into the boat? And he says, let me check, Jason. So I said, okay. And he disconnects the shore power cord, and he grabs his Amazon.com super inexpensive voltmeter, And he sticks his meter leads in the end of the shore power cord, and what do you know? He has a low quality multimeter, and his meter leads are not long enough to reach inside the end of the shore power cord. So I give him my fancy multimeter, which has the extra long leads, which will get right down inside of that thing and tell us exactly how many volts are coming out of that cord. So he takes my meter, my fancy meter, and he plugs it into the end of the shore power cord. And he said, I'm getting 120 volts. I said, okay, good. Now are we getting 240? And he swaps the meter leads around, and what do you know? We're not getting 240. And I said, come on, man. I said, come on. I said, you told me you spent 6 hours on this, and we didn't check the cord. And this is what I meant by he was humble. I had to bust his chops a little bit, but he was okay. He was okay. He was good. I said, look it. I said, we don't have our 240 at the cord. I said, we got to go back to the pedestal. That's the next check. So we go back to the pedestal where the other end of the shore power cord plugs into, and what do we have? We have 120. We don't have 240. And so I said, okay, there happened to be another pedestal that wasn't being used. We went to that pedestal. We measured that pedestal, and that pedestal was working. We had 240 and 120 volts on that pedestal. So we swap our shore power cord to that pedestal. We plug it into the boat, and the 6 hours of troubleshooting that he said he did to deduce that this $6,000 plus labor isolation transformer, that he really had no business or no education in troubleshooting, was working. It was now functional. It worked. So for that extra 10 or 15 minutes worth of work, we already have a six-figure estimate. There's 6,000 plus labor that comes off of it. Thank you all very much for your time. I hope you all learned something. If you have any questions, I'll be here for the duration of the seminar. If you'd like to reach me directly, you can call me at 239-600-0605. For technical related questions, you can email me at capemarinesurvey@gmail.com. For claims related questions, you can email me at jason@pilotmarinesurvey.com. We also have offices in Pennsylvania, Ohio, Norfolk, Virginia Beach, Beaufort, Wilmington, North Carolina, Charleston, South Carolina. I run the Southwest Florida, Fort Myers area office, and we do have a seasonal office in the Florida Keys.